screen. Okay, we see it.
Thank you.
Yeah, this is again a 20 plus 5-minute talk, and I'll give a 3-minute warning after 17 minutes. So looks good. Go ahead, please. Thanks.
Excellent. Thank you very much. Thank you for the organizers. It's a great pleasure to be here. And today I'm going to talk about RLID stars and in the context of the Kepler mission's first primary mission. I will talk a little bit about the Kepler spacecraft or the mission itself, although I think I don't have to introduce it. I will talk about RLID observations and results. I also will mention one ongoing projects and first results, and I have to be quick because I would like to announce 2 conferences, and I need 1 minute for that. So the spacecraft itself is a 0.95 meter aperture Schmidt telescope. You can see it still on the ground. It observed one particular fixed sky part for 4 years, from 2009 to 2013, in the visible wavelength range, and used almost 100 megapixels. And this is the nice camera set that produced all those wonderful data that we are going to talk about those. So the Kepler, of course, is or was a exoplanet discovery mission or machine, and it found a lot of interesting stuff, delivered half of all confirmed exoplanets, which is the total number is over 5,000 by today. But it also did, I would say, revolutionized the field of astroseismology and also classical pulsators. I will show a few examples. It found a lot of eclipsing binary transients as well, and did some solar system studies as well. What are the key ingredients, the most important factors that added to the success? I list here 3. One is the large number of stars that were observed, close to 200,000 simultaneously with the same cadence. And the second thing is that this monitoring was done almost without interruption. So I would say quasi-continuous, because of course there were small gaps for data download periods and some technical issues. But other than that, 4 years of data, which is unprecedented. And one of the most important thing is the third one. The observations were done with extreme precision, 10 to the -4, 10 to the -6, at least 2 order of magnitudes better than anything that was delivered regularly from the ground. Of course, you could have something like that from the HST, but you know, that's an observatory. You have to do a lot of observations, but Kepler did it for 4 years at a specific part of the sky. So this is the improvement that was shown by Katrin Kohlenberg in one of the early Kepler papers. And on the left, you can see an RLRA, a dedicated ground-based campaign with 6 observatories on the ground along the globe. And on the right, you have the Kepler data, the first Kepler data, a few months of data. And you see how much better the coverage is on the top, but on the bottom you can see the improvement in the Fourier spectrum, which is again these individual measurement points have 1,000 times better precision. I also would like to show one example that there were very strong debates before the space photometric era about how to classify different RLID stars in terms of extra frequencies, periodicities that were found in the Fourier spectrum. This is one example from an early Macho paper. So the question was, how many frequencies can you detect in a modulated star? For example, we're talking about Blaschko stars, whether you see 1 or 2 extra frequency components on which side or on both sides, whether you see a triplet or quintuplet, things like that. So that was a strong debate for years. And if you take one space photometric observations, now this is a specific example from Corot, a little bit earlier than Kepler. What you can see here is a beautiful Fourier spectrum You can even see on the left, on the lower frequency regime, the Blasco frequency and also its harmonics. So it's not sinusoidal, it tells us. And also it's just resumed on the fourth harmonic of the main pulsation of this modulated RRAB star, V1127 Quille. And what you can see is that you see an infinite series of these side peaks. So not one, not two, not a triplet, not a quintuplet. So if you can see many of them on both sides. And in fact, if you go to the mathematics of the modulation, and there's a beautiful paper led by Josef Benke more than 10 years now. If you have a modulation, and if you are familiar with radio transmission theory, exactly that's what we are doing here. You know, we have a signal and we modulate it either in phase or in amplitude. And the mathematics tell you that that's what you would expect. There's an infinite number of side peaks with the frequency difference of the modulation period and so on. And that's exactly what we see here. So there is no debate anymore on that aspect. There is one catch here, however. This is pure mathematics. It doesn't really tell us much about the physics, but that's just an example. So Kepler data started to pour in, and you can see here, I will show a few examples of Blasco modulated stars. These are beautiful. And you don't really see here the individual pulsation cycles. These are 250 days or more than 200 days of data. But what you can see that on these two examples, that the consecutive modulation cycles are quite different from each other in amplitude, maybe even in shape, and even the modulation period can change from one cycle to the other. So this tells us already that whatever causes Blasco modulation, it's not a strict geometric or very regular phenomena. I will show these zoo early Kepler Blasco RRIB stars light curves, and this is close to the 4-year thing. You can see long modulation period, you can see short modulation periods, you can see large modulation amplitude, small ones, very irregular ones. We even found modulations with multiple periods, 2 periods or 3 periods that you can see on the top in the middle, for example. So this is really beautiful when you can see it like that, 4-year uninterrupted data in most of the cases. Here I show 2 Blasco stars. One is this already mentioned Coro example on the left, and on the right is RLR itself from Kepler early data. This is also quite beautiful just to see these continuous data and what Blasco is doing. You can see the phase modulation as well as the amplitude modulation here in both cases. This is RLR itself. Short cadence data. So there's a data point every minute. So what I'm showing here is about 3 years of data containing more than 1.5 million measurements. Of course, you don't see the individual pulsation cycles. What you can see is the Blasco effect, the well-known Blasco effect in the eponym, in the prototype of RRAB modulated stars. And it's just fascinating. I don't know, I could talk about it for an hour. You can see that it starts with large modulation and it goes crazy. The modulation amplitude decreases. Also, the Blasco period changed by 2% by the end of this period. And you can see that it's not really regular. It's doing interesting things. So this is very nice to see that kind of changes in the Blasco on the long term. There were interesting things that we found. One is an interesting, well-known dynamical effect, the period doubling, which is the alternating maxima and minima and light curve shape that we can see here in the Kepler light curves in modulated RRAB stars only. In the frequency spectrum, what we can see is the half integer frequency between the main position frequency and its harmonics. So that's what tells us that there is something going on here. It is well known from higher luminosity stars, type 2 Cepheids and things like that, but it has never been seen from RLI type stars. If you think about a typical half-day period RLI star, then you can easily understand that from the ground it would be extremely hard to see that during one night, because you will see every second cycle and you will miss this kind of alternation. But this is very important because period doubling is the route to chaos from regular dynamical motion. So that's pretty interesting. We see strong period doubling in certain sections of the light curve of RLI stars, modulated RRAB stars, not in all stars and not always, but I will show a few examples. This is RLI. When we zoom in, RLI itself, you can see this alternation throughout, almost throughout the whole light curve. There's even a larger zoom down here. You can see, and maybe this is almost the same thing. You can see how different are alternative maxima and also the light curve shape. If you want to see the change because of this variation in the bump shape or the hump shape, that's the thing to go and take this light curve, and you can see that they are really different. And the interesting fact is that the difference between consecutive maxima is close to 0.1 magnitude or even higher in the case of RLI. I'm talking about RLI, the prototype itself still. So this was very surprising and very interesting. But we went on and we succeeded to reproduce this kind of period doubling thing with a 9:2 resonance between the fundamental radial mode and a 9th radial overtone, which is very surprising. We checked a lot of different resonances, but this is the one that explains period doubling. And the late Robert Bushler and Zoltán Kollát even showed that this kind of resonance can cause a stochastic or regular modulation as well. So if you have this kind of resonance, and you can see the main period, the main periodicity, the A, this is the fundamental, and then B is the additional one, the high radial overtone, and the 9th one. Then you can see that it can cause some kind of modulation as well. And indeed, Radek Smollett and Pavel Moskalik demonstrated in actual hydro models in BL-Hercules stars that this kind of resonance, half-integer resonance, can cause modulation. So this is a strong indication that it has to do something with the Blaschko effect, especially that we saw period doubling and resonances only in modulated stars. We checked the Kepler stars with that kind of precision, the non-modulated ones as well, but we haven't seen anything like that. This is still RLI, the prototype. And what can we see here? That besides the half-integer frequency that tells us that there's a resonance in action, there's an additional signal here, very close to the predicted first overtone. So, and our hydro models also demonstrated that it's indeed possible that there's a strong indication that RLI itself, this is a prototype of RRAB stars, is pulsating in free radial modes. So it's pretty interesting. Of course, this signal has an amplitude 100 times lower than the main pulsation mode. Of course, that's another reason we haven't seen it before Kepler. And what about the Blaschko modulation and its cause? I won't make any justice here. I just put here these very nice figures by Katrin Kohlenberg, and it just lists the possible explanations that were proposed during the last century or the recent decades. Of course, we have this oblique rotation model. We had the resonance model between the dominant mode and the non-radial mode. Of course, Stutter's idea is also interesting, when the variable turbulent convection would cause the modulation of the amplitude, and even shocks were invoked to explain these modulations. And we have now a a fifth one, that's the radial resonance between the fundamental mode and a high radial overtone. And as you could see, we have hydro models actually that prove that this might be in action, maybe not in all cases, but that's a strong candidate at least. Let's put it in that way. I won't say too much about additional modes. I think Laszlo, after the coffee break, will say a few words about that, but it's very interesting that if you have that kind of precision in photometry, then you can see a lot of interesting low amplitude additional modes or additional periodicities. A few years ago, we have seen things like that on the Petersen diagram in case of overtone pulsators, both in RLRA and Cepheids. You see these three ridges with a very prominent period ratio of 0.6, 0.61, or up to 0.64. And on the right-hand side, what you can see is we just published a paper, and in RLRA stars and RRC, containing RRC and RRD stars, there's a lot of extra frequencies around that period ratio. This is a whole new field. Of course, OGLE, we can see that kind of additional modes in OGLE and the ground-based photometry as well. But if you have a very nice precision with just like Kepler, then there's a lot of other things that you can do. One thing is here, the additional periodicity is found in modulated RRAB stars, a very nice figure produced by Josef Benker. What you can see here is Fourier spectra of Kepler modulated RRAB stars between the fundamental mode on the left and its first harmonic, the twice as much frequency on the right. So in between, usually you wouldn't expect much, but we see a lot of things here. In the middle, you can see half integer frequencies for the modulated stars showing the period doubling. You can see frequencies around the predicted first overtone. This is F1, the yellow band, and also around F2, which is the predicted second overtone. And it's very interesting to ask whether these are radial modes or non-radial modes excited around these frequencies. Both scenarios are possible, but at least in one case in RLRA, as I mentioned, we do have evidence that that might be a radial overtone excited with a low amplitude. So this is very interesting. And the last couple of slides is the Kepler pixel project. So we had a few dozens of RLRA stars in the original Kepler field. We wanted to have more. And what we did with my PhD student is to took all the background pixels of Kepler. As you know, these main targets were downloaded only 5 or 6% of all the available observed pixels were downloaded because of bandwidth constraints. But there were a lot of background pixels around the main targets that have never been scrutinized. But if you have that kind of precision, it's expected that interesting faint variable stars, transients, and so on can be seen. And that's what we did. We systematically went through 6 million pixels and found 26 new RR stars. Some of them are Blushko, 3 RRCs, and 2 RRDs. It's important because we didn't have any RRD stars in the original Kepler field. So these are additions. Some of them were found in Gaia as well, and Penn stars, 5 or 6 are brand new that were not identified in other surveys. But here we have 4-year data for these faint stars, and that makes it very important. You can see that the already known stars with gray and the new ones in blue very nicely complement each other. Now we are in the halo regime, so we can see the fainter ones that were missing from the original Kepler field. Let's say a few words here. So if you are interested in these light curves, the textbook light curves, you can go to our website. My research group has published all this data, Kepler, RRAB, RRC stars, also Coro and test light curves. You can download all this here from here. And one of the conferences I want to advertise is the RLRA conference that was started in 2015. The next edition will be in La Palma in September, and registration is open. You can find this website and register. That will be a physical conference. And another one a bit later next year in April, we had to move that IA symposium on period luminosity relations. So maybe you are interested in that one in April in Budapest, Hungary. That will be preceded by a spring school a week earlier. So thank you very much. Thank you for your attention.
Thank you. Okay, Mario has a question.
So it's just spectacular data. I was just curious though, in the sample, what is the fraction of what you would call unmodulated stars compared to the modulated sample? Are any stars unmodulated at this point with this kind of precision?
That's a very good question. So at the beginning, when we started to see this data, it was kind of easy to decide. And we got this kind of canonical ratio of 42% of the RRAB stars are modulated, something like that. And of course, I'm aware that there were claims that, for example, with K2, the second mission of Kepler, maybe this is much higher, but I think there are a lot of problems with those claims. There are technical problems, technical issues. So I would say that what we see is 40, 40 to 45, something like that. So this is a very nice alignment with the result of the Konkoli-Blaszko survey that was conducted a decade ago by Johanna Jurczyk and her team. And what is interesting, though, that those non-modulated ones are very, very stable, but not constant at that level. And Josef Benke, I think he's on the call, he had a paper on that, and he tried to investigate those stars. So they are showing something. They are kind of stochastic beyond, if you have a very regular unmodulated fundamental mode pulsation. But if you go to into the noise level and subtract these, so you do see some kind of variations. So they are not completely unmodulated, but those variations that remain are quite low amplitude and kind of stochastic. So if I remember correctly, they don't really find any very regular variations. So I agree at that level. For example, all the stars that Kepler observed are variable stars. So it was very hard to see any that are completely flat. So I think there are a few A-type stars that are very quiet, but other than that, you see stellar spots, very small ones. You see all kind of things. All these stars are variable stars at some level.
Horace has another question. Please go ahead.
Hello, very interesting talk. In the case of the field RLRA star XC Cygni, there was a pronounced change in the Blaszko period that was associated with an abrupt change in the fundamental mode period. Do you see any stars where there were correlations between the Blaszko period changes and the primary period in your study?
So in this case, I only touched on the primary mission of Kepler, and we had only 50 or so stars plus these 26 that we added. Half of these are, I don't know, 80% of these are RAB, half of those are modulated. It's a small sample, kind of. So I haven't seen any abrupt changes like that. But K2, the second mission, and maybe Laszlo will talk about a little bit that after the coffee break, it has thousands of RLRA stars, and tests added another, I don't know, 1,000 or so. So that's a much bigger sample. And if there's anything, we just started to scratch the surface of those, haven't analyzed them in detail, but it's on the list, and we will do that. And if there's anything like that, like XZ Signi, then we should see that on those in those lines. But although those are much shorter, I would say I was talking about 4 years of data, but in K2, in case of K2, most of the cases you have 80, 90 days, and with TESS, it's typically 27 days, except the continuous viewing zones where you can have up to 1 year, but much shorter. So yeah, so these are the factors.
Thank you.
Any last questions from the audience? Okay, if not, let's thank Robert and all the speakers again. And we'll be back 10 past the hour.